This call is now being recorded.
This video is in continuation with the previous video. Actually, the last video was interrupted, and we were discussing the diode current equation. And now we have modified the diode current diode current equation, Shockley, which is the Shockley equation. We have calculated the value of this Q by KT, which is equal to 40 at the 27 degree Celsius. Now we will put some VD value. So if I put a value VD equal to let us say minus 0.1 volt. So minus, if I am putting VD equal to minus 0.1 volt, then definitely the meaning of this negative voltage is this, that I am reverse biasing the diode. Basically, VD is the voltage across the PN junction diode, and if I am providing a negative voltage, then basically I am just reverse biasing this diode. And now we will try to calculate this ID. This ID will be equal to I naught e raised to the power 4, because this 40 into zero point 0.1 volt, negative 0.1 volt, and this is minus 1. This is minus 1. You can see here, this is minus 1, 0.1. And if we are calculating this, I naught, this is 1 upon e raised to the power 4 minus 1. And this term, 1 upon e raised to the power 4, is very less. And we are multiplying this term with the I naught. Okay. And which is of order of microampere, which is already with the power of 10 raised to the power minus 6, which is of order of 10 raised to the power minus 6, and we are multiplying this with the I naught, which is 1 upon e raised to the power 4. If you will try to calculate it with the help of a calculator, then you will get a value like 0.01. So, and we are multiplying this with 0.01, and multiply by 10 raised to the power minus 6. So this term will more reduce, and we can neglect this thing. So we can neglect this thing, and we are multiplying this I naught with here I am writing this ID is I naught e raised to the power minus 4 minus I naught. So you can see here this e raised to the power 4. If you calculate the e raised to the power, we know the value of e is between 2 and 3. It's like between 2 and 3. It is like 2.7 something. So if you will try to calculate this, then you will get this like 54 something. E raised to the power 4 is 54 something. So we are reducing this I naught 50 times. Okay, so we can neglect this term because the value of this term is very less, 0.000 something. So we can neglect, and this is in microampere. Okay, so we will neglect this thing. So you will get ID equal to minus I naught. So here you can see in the reverse bias, the diode current is VD equal to 0.1. So, the diode current is equal to minus I naught, and which is the reverse saturation current in the reverse case. So, with the help of this equation, you can understand, and definitely we have used an approximation. And what you need to understand at this point, in electronics and electrical engineering, you will find many approximation. And I have told you before, the electrical and electronics engineering is all about proportionalities and approximation. So we need to understand the proportionalities between quantities, so how the other quantity is varying with the variation in the some quantity on which it is dependent, and how the approximation, how can we take a valid approximation. Here you can see we are reducing this 50 times. So 50 times, 100 times are the valid. Something is if something is 100 times, 50 times, then this is a valid approximation. Okay, so we are reducing this 50 times. Okay, dividing by 50. So that could be a valid approximation. So id equal to minus I naught. So the direction is definitely reverse, and the current value is minus I naught. So first thing is validated. We have validated the reverse bias value. Now we will try to find out at the 0 volt. What will be the value at the 0 volt? And if we put 0 volt, you can calculate. If Vd is 0, then this if at Vd equal to 0 volt. Let us suppose we have applied 0 volt. Then what will happen? The Id must be 0, and we can see this thing from the equation. If this Vd is 0, then the numerator is 0. Then whatever is the denominator doesn't matter. Then this part is 0. Then e to the power 0 minus 1. You can see here Id equal to I naught e raised to the power 0 minus 1, and anything raised to the power 0 is 1, then this is equal to I naught into 0, which is 0. And now we will try to calculate and we will approximate this equation, and again we will try to calculate the value of diode current at some positive value of the voltage. I will send you one or two numerical related to this equation. This equation now you are familiar with this equation, and in most of the cases this eta will be equal to 1. So you can take this eta as 1, and now I will give you a further approximation of the equation. Okay, so now what we are doing, we will try to calculate the value at some Vd equal to Vd equal to 0.1 volt. Let us suppose the positive 1 volt we have applied. So what is the equation? Id equal to I naught e raised to the power 40 times 0.1 minus 1, and this e raised to the power 40 is now e raised to the power 4 minus 1. Again we can take the approximation here. This term is increased almost e raised to the power 4 times, when the value of e raised to the power 4 is approximately equal to the 55. If you will calculate with the help of your calculator, then you will find we are increasing this term 50 times larger than the remaining term, which is of order of 10 raised to the power minus 6. So here we can approximate this term. We can approximate this term, so we can remove this minus 1, and Id can be written as I naught e raised to the power 40 Vd. So this is the approximation of the equation. Now, and this you can use for the numericals. Okay, now we have reduced the complexity of the equation. We have taken some approximation, and you can understand one thing. If I will increase this voltage, then what will happen? If this is 0.2, then this will be 8 here. Now you can see the value is increasing, and if this is 0.3, this will be 12. So you can calculate e raised to the power 12. Let me calculate for you e raised to the power 12. Yes. The value is very large. It's like 162,754. You can see this on my calculator. So the value is increasing. So definitely this approximation is very valid. because I have just taken a value randomly. I have chosen a very less value 0.01 volt. Okay, and you can see at 0.011 volt even we can approximate. So definitely for any higher values which we are applying across my PN junction, and definitely you know that we will apply more than zero point 0.1, 0.2, 0.7 because there is a potential barrier of 0.7 volt. So you need to understand, if you are applying a zero point 0.7 volt, then definitely e raised to the power 28. Then this term will be much larger. So this term will be much larger than this I naught. Okay, so then we can approximate. So this equation is equally valid. So what we need to understand, for the forward biasing, I have approximate the equation like this: 40 VD. But you need to remember this thing. This 40 I have calculated on the basis of Q by KT. And I have taken the value of T at is 273 plus 27, 300 Kelvin. At 300 Kelvin, and if in numericals that some value of the temperature is given, then you will have to calculate the value of Q by KT according to that. Okay. So here we conclude the discussion of diode equation. Okay. So what you need to understand one thing, that if I am using this diode in the circuit, let us suppose I have a circuit like this, and I am using a diode here. I have applied some voltage. So in this circuit, I cannot use this equation. Why? Because of the non-linearity of this equation. As we know, the conventional circuit theory, in the conventional circuit theory, all the theorems are applicable for the linear element. If you remember the statement of Norton, statement of Thevenin theorem, then they require linear and bilateral elements, and here we do not have a linear and bilateral element. Okay, so what you need to understand, uh, this is a unidirectional element, and and this is not a linear element. And if we need to use this equation, let us suppose if we are using this equation, then we have the equations for the other elements, like this resistor is a linear element, and the battery has a characteristics of like this. Even though if we look at the signal and system point of view, then this is not a linear thing, but the it is a constant value. Okay, and for the resistor, the characteristics is linear. The IV characteristics of a resistor is linear. So you can understand the IV characteristics of a resistor is linear, and and with these linear elements, if I am using one non-linear element, then it will be a very complex job to find some solutions. Okay, so we cannot find the solutions just by using the algebraic manipulation as we do in the normal network theory. In normal network theory, we use the mesh, and we use the nodes, and we use the loop analysis, node analysis, and then we can find all the voltages and currents inside the circuit. But here, using this equation, it will be very difficult. So we can find this thing with the help of numerical analysis. But as and the numerical analysis is a part of mathematics, and it is for the graduation. And in graduation, it is taught to the BTech students. So ID equal to I naught e raised to the power VD eta VT minus 1. So this is a non-linearity here, non-linear equation, and we cannot use this non-linear equation with the linear equations, and because the validity of theorems and the complexity of the equations. That is why we go for the different approach, and that different approach is the modeling of diode. Now we shall understand the modeling of diode. Okay, so next is the modeling of diode. Here you can see the characteristics.